morning. Thank you for your prompt return from the coffee break. I know that can be tricky. And welcome to our session this morning, where we're going to be talking about artificial intelligence for accessibility. So the way we're going to organize this session is, after some brief introductory remarks, each of our three panelists will be giving a short presentation to set the stage about their research in specific application areas of AI for accessibility. And then we'll actually be doing a panel-style Q&A. So we have some starting questions to kick off discussion, but we really want to make this an interactive session with the audience. So please, as you're hearing the presentations, make some notes about questions you'd like to ask the panelists, and we're going to be sure that more than half the time in the session is for dialogue back and forth. So just as background, why is it important to think about accessibility as a topic domain for the application and motivation of AI research? Worldwide, more than 1 billion people identify as disabled in some way, according to the most recent World Health Organization statistics. Just within the United States alone, recent census data indicates that 1 in 5 adults has some kind of a disability. And of course, besides permanent disability, there are a whole spectrum of ranges of special needs to consider. So for example, people might become temporarily disabled, perhaps with a broken limb, or even situationally disabled. Perhaps if you're driving your car, then you're not able to use your visual attention, or if you are pushing a shopping cart or stroller, you're not able to use your limbs. So when we think about disability in this more temporary and situational sense, the range of people who can be helped when we think about accessibility applications becomes even broader. This is a priority for Microsoft as a company. So our CEO, Satya Nadella, shown here in this really cool cutout headshot, in his email to the company a few months ago, one of the things he said was, as I think about living our mission, top of mind for me is how we must make Microsoft products accessible to the more than 1 billion people globally of all abilities. Universal design is central to how we realize our mission, and I will continue to devote my passion to this priority. And I think that thinking about how advances in artificial intelligence can help not only Microsoft, but the entire technology community move forward on addressing some of these very impactful challenges is a really exciting and timely topic to consider. Our Chief Accessibility Officer, Jenny Lay-Fleury, put together this slide that I wanted to share with you because I think it helps give an overview, not complete, but a good overview of some of the key topic areas in accessibility that we can begin to think about as challenge areas to address with AI technologies. So for example, from Microsoft's perspective, company-wide, we think about 6 main categories of disability that our technologies are trying to address. And those include visual disabilities, hearing disabilities, cognitive disabilities, which I think is a really interesting one that doesn't always necessarily come readily to mind, but is a really large and growing segment that people are becoming aware of. Speech and communication disabilities, motor and mobility impairments. And then this last category, I know Jenny struggles to come up with a good name for it. And again, this is a topic that's just beginning, I think, to come to many people's awareness. She's the term neural, and she's trying to refer here to conditions such as post-traumatic stress disorder, anxiety, depression, and thinking about those conditions as well, and how technology can help people to better manage and deal with those types of situations. And of course, this is a somewhat simplified taxonomy of disability. So of course, many people might have things from conditions from across several of these different categories. Certain kinds of illnesses or medical conditions might result in different combinations of disability. So for example, people with ALS, such as Stephen Hawking, have a condition that causes motor disability, but then because of the impact of that motor disability, that also impacts their ability to produce speech. So you would have a combination of motor and speech needs. And all of these, I think, are really rich areas for thinking about the application of AI. And so our panelists today, we're lucky to have with us, are all internationally known experts in accessibility research and have all begun to use both automatic and human-in-the-loop AI techniques to try to address some of these challenges. And so Jeff Begum is a professor at Carnegie Mellon University. And today he's going to be talking to us about applications of AI for augmenting the sense of vision. Walter Lasecki is a professor at the University of Michigan, and he'll talk about how AI technologies can be applied to augment hearing. And finally, Sean Kane, who's a professor at the University of Colorado, will talk about how AI can augment speech and communication. And again, after each of them give their presentations, we'll do a little bit of time for individual questions if you have a question that's just specific to that presentation. But then as a whole, the panel, including myself, will be happy to discuss with you kind of larger thoughts around themes that you see across all the presentations and around what are the interesting challenges. How can AI research inform advances in the creation of accessible technologies, and how can the needs of accessibility really help AI research push the boundary in setting its agenda and defining what good problems and metrics are. So I'd like to invite Jeff up first to share his presentation with you about augmenting vision.
Thank you. All right, I'm Jeff Begum from Carnegie Mellon University. Thank you, Mary, for the great introduction. And so I'm really excited to be in this panel. I think it's really great that Microsoft not only is doing a lot in accessibility, but also including us in AI and an AI-oriented summit. And to me, this makes a lot of sense, right? Because AI has the potential to dramatically expand the possibilities for people with disabilities, making the world more accessible. And people with disabilities have been among the earliest adopters of AI technology and have driven some of the biggest human-facing innovations in the area. I think there's a lot to learn from their experiences. I think that when we develop AI-driven approaches for mainstream use, so as AI makes it out into the world, there's a lot that we can learn from the early adopters. And I think people with disabilities have been the earliest adopters. And so in my short talk, I'm going to focus on what we've learned by deploying a crowd-powered system for people who are blind to answer visual questions. Let's see. Sorry. My view is just not syncing, which is weird.
It's right up there.
Yeah, right. All right. All right, so if you think about it, developing technologies for people who are blind should be a grand challenge for computer vision research. I think what is more common to computer vision as a discipline than a natural application that reproducing in software the perceptual abilities afforded by the human eye? And there's actually been a lot of research in this area. But sometimes it's been a bit of an afterthought. It's, I've developed this cool new computer vision technique. I wonder if a blind person could use it. I bet they could, right? And so a few years ago, some students, sorry, it's just when I click the next slide, it doesn't do that.
Let's try that again.
Oh, wow, this is much better. Yeah, this is perfect. Okay. Thanks a lot. Okay. So a few years ago, my students and I set out to discover what would blind people actually want to know if they could ask anything. And we did that by deploying this mobile application called VizWiz. And so to use it, users take a picture, they speak a question, and then they receive answers back pretty quickly from people we've paid out on the web to answer those questions, so crowd workers. Great. So we deployed this application. We've had more than 10,000 users answer or ask over 100,000 questions with it. There's a wide variety of questions. I can't go over all of them right now, but just to give you a sense, right? So we have everything from, what does this thermostat say? To how do I cook this? Believe it or not, you can actually find the cooking instructions for this packaged food here on this photo. Kind of weird. There's a photo here of a nighttime sky. And it's really interesting when we saw this, somebody was asking the same question, what does the sky look like? What does the sky look like every 5 minutes? And we were like, what is this person doing? But around that same time, we were monitoring Twitter, and we saw that somebody posted, I just used VizWiz to watch the sunset, right? And so someone had used VizWiz by just querying over and over again to ask to watch the sunset, which is pretty cool. Oh, there it is. We get a little bit of stuff that we didn't exactly intend and discourage, like that credit card there. We get a bunch of credit cards sent to, for interpretation by the crowd. We also get a lot of appliances. So this is a coffee machine. It's kind of hard to answer in this form, but we get a lot of how do I use this device? All right, last one, I think. Maybe. Didn't work. But anyway, so we got a lot of questions asked, a lot of images, and we were able to package this up into a data set. So we removed those that contained personally identifying information, and we still were able to release a data set of nearly 50,000 images, questions, and answers. And our hope is that this data set of real questions by blind people in their everyday lives may inspire computer vision researchers to work on this problem, and maybe even make it a true grand challenge for computer vision. And so when we were getting started, I talked to people. So in 2011 or so, I talked to computer vision researchers. I said, you know what, I have this application, and we're generating this data that I think would be really interesting for you. And they said, oh, wow, that's pretty cool, but that is way too hard, right? Because you look at the diversity of questions and the poor quality of the images and whatnot, and they said it's just too hard. But fortunately, deep learning has come along, and the data set is still really hard, and we're really far from being able to answer many, if not most of the questions automatically. But fortunately, with deep learning has come confidence. And if nothing else, I'll take that, because people have started to work on this. And so now there's a number of papers out have used our data set in serious ways to address this problem. And that includes Microsoft's own Seeing AI, which is a cool new app that was released a few days ago. And so if you haven't seen this, I encourage you to check it out. So it's for the iPhone. It does all kinds of cool things with answering visual questions. One of the things that the data set allowed us to do was to kind of understand problem areas, more task-specific problem areas that blind people wanted to know more about. And so one of those that we noticed was that a lot of people ask questions about devices. So we got a lot of pictures of devices, printers and washing machines and coffee makers and vending machines and things like that. And VizWiz, the way it works, it's difficult to describe to a person all of the different buttons that are on an interface. And it's even harder, especially as the interfaces for these devices have become flatter, for a blind person to independently find the button that they might want to on an otherwise just flat surface. And so we developed a system that targeted this particular use case, and it modified the VizWiz workflow just a little bit. So users still started off by taking a picture, in this case, taking a picture of the interface that they wanted to use. And then crowd workers, instead of answering a question, would label that interface. So they'd provide labels for all the different buttons on the interface. And then that allowed us to create a computer vision model that ran on the phone that would tell the user, as they held the phone up, what button their finger was under or over top of. And this works really well, and surprisingly well, because we weren't trying to solve a general computer vision problem of answering anything out in the world. We were actually not even trying to solve the general problem of how do you use any individual interface for a device. Instead, we're solving the problem of, given a labeled model of this particular interface, taken from roughly the same perspective and roughly the same lighting conditions, can you tell the user what their finger is over top of? So here's just a little bit of a description of how this works.
Business users capture a photo of an inaccessible interface and send it to multiple crowd workers who work in parallel to quickly label and describe elements of the interface. The business application helps users recapture the interface in the field of the camera and uses computer
Sorry, I'm not sure why the video is not showing up on there.
Oh, it did. It did. It did.
Oh, sorry.
vision to interactively describe the part of the interface beneath their finger.
All right. And like I said, it works pretty well. We tried it across a number of different kinds of interfaces. So here's just a short video of some things we tried.
J and H, near A, B, B, C, C and D, C, 3, 3, 4 and 3, 5, 6, 6,
Copy
9,
machine.
9, 9, enter, 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 sample copy, near sample copy, energy saver, 2, yes, yes, done, done and yes, done, near 7, near back, 7, 8 and 7, 7, 8, 8 and 0, K, left, down, power, near power, up, down and up, down, pause, start.
So I really like that last one, the laser cutter. Depending on the audience, sometimes people are like, oh, a laser cutter. But of course, why not? Blind person can use laser cutter. That's great. So that worked pretty well, and we're hoping to deploy it. And it's not that AI computer vision couldn't eventually take over this task, but with the crowd, we're able to get there pretty fast. We're able to generate data that the computer vision can then train itself on. And we're actually able to understand a little bit more about what's important in facilitating this kind of interaction. We also modified this slightly, and instead of having the user just take a picture of the interface, we had them take a picture of the interface alongside a dollar bill. And this allowed us to do two things. One is it allowed us to help the user aim the camera because we had a fiduciary marker of a known size, and also allowed us to help to actually create a model of a particular size of the interface so that we could generate a tactile overlay on top of the interface that the user could attach. So I'll show you how that works in a couple of videos here. So here's the user. They're going to take a picture of the interface. And because we have this dollar here, they're able to get some assistance in aiming their camera. Actually going a little bit back farther than just including the dollar, because they know they have to go more than just including the dollar. Apparently aiming is good. When they take their photo. From this, we're able to automatically create a model. Look, it spins around. A tactile model that then can be sent off to a 3D printing service. So here's our 3D model being printed. And then independently attached to the device with adhesives by the blind user. So kind of imagines a different future where people are able to, with computer vision and a little bit of crowd support and maybe some services that they can access on the web, create more accessible devices in their own homes. All right, so by releasing this general purpose crowd-powered system, VizWiz in this case, we're able to motivate a number of different lines of research, both computer vision on the hard problem of answering arbitrary general questions, but also research into a system that combines the user, the crowd, and computer vision to target a specific task. And this experience has led us to some generalizable thoughts, I think, for AI systems and the research in the future in this area. And so I'll illustrate this with a sequence of videos from Justin Romack, who is a blind blogger who pretty early on in the project, around 2011, recorded a video of himself using VizWiz to answer a question. And despite it being a little bit old, I think it contains examples of themes that we've extracted from our experience. So here is Justin asking his question.
I've got my thermostat here, and I've set it way down, and I'm going to take a picture here. So place this, move it back a little bit. Take a picture, and I'm going to record my question. What does this thermostat say?
All right, so one thing we noticed pretty quickly is that it's difficult for blind people to take pictures independently. But despite that, a good picture is vital, whether you're sending it off to a computer vision system or to a human-powered system. And so as a result, we and others have done a lot of work on blind photography, supporting blind.
So, place
here's
this,
the
move
picture.
it back a little bit.
Supporting blind photography to enable blind people to take better pictures. And so I think the lesson here is that it will still be a while until AI systems are able to take over many tasks fully. But AI can be useful now to support and amplify what users are able to do. And so in this case, computer vision has been pretty useful in helping blind people take better pictures, even if it's difficult to answer general visual questions automatically right now. So here's a video of Justin getting his first answer back for his question of what's the thermostat say.
So let's see, it already has some answers available.
Thermostat, engines.
The IQ Engines has it labeled as a thermostat, so we knew that. That doesn't do me too much good.
All right, so of course Justin knew that this was a thermostat. And so we had sent off the picture at first to a system that just told them the main object in the photo, right? And surprisingly, it actually worked, right? This is a few years ago, and this is also sort of human-powered. But I think the lesson here is that there's been a lot of effort in providing fairly generic labels for images. For instance, Facebook has this really cool thing where every photo now posted to Facebook comes along with keywords. So you can look in the alt text for Facebook's images, and you'll see that they have keywords. And this is great, but I think we need to look past beyond just providing labels and look at what people actually want to know. And a lot of times, the things that they know, they want to know are much more contextual, right? So working with what the users are able to kind of infer on their own, and maybe what added information the computer vision systems can provide. And then finally, Justin gets an answer back from the crowd.
Just hang tight here. It did identify
Answers available.
the temperature
One on the
earlier.
left, 71 on the right. I don't know which is the current temp and which is the setting. Web worker.
Okay, a web worker said that 75 is on the left and 71 is on the right. They're not sure what the current temperature is. I can tell you that 71 is what I have it set at.
So what I think is interesting here is that the crowd, the human workers, were also not able to tell from the photo what the current temperature was. But they were able to appropriately convey their inability to do so and provide Justin with extra information to figure it out. So here I think what's important is that errors are important and not all created equally. So a lot of times I think we have the tendency to report, say, accuracy numbers. But depending on the type of error, it can be much worse or better. And I think we also need to think about how do we measure and express confidence, right, as part of this. And so for this, I'm really inspired by work that Mary did here at Microsoft Research and others in looking at how blind web users reacted to different captions provided to social media images. And so there's an example here of, it's a picture of Hillary Clinton, and the correct caption or a correct caption would be image shows Hillary Clinton walking onto a stage in front of a large crowd of people. But if you told blind people in a user study that the caption was actually a man doing a trick on a skateboard at night, and they didn't have other reasons to believe that that wasn't true, they would come up with a justification for why that might actually be the case, right? And so there's a cost to errors, and thinking about what that cost might be and how we minimize it, and also how we can measure and express confidence. A lot of times the models that we make for the computer vision or other AI tasks output some confidence value, but there's not been a lot of importance put on making those confidence values match up to user expectations or expressing them in a way that users can understand. So just to summarize, the things that I would like to see more work on, and I think are important as we increasingly see AI make it into user-facing applications, are systems that amplify users with AI support instead of trying to do everything. Figure out ways to augment the person, amplify what they're able to do. Figure out a way to target our work towards solving real problems, right? So labels might be really interesting and useful in some cases, but a lot of times what we really want is something more contextual. Embrace and understand errors and figure out when are the errors important and when are they not. How do we reduce the cost of making errors? And part of that is probably measuring and confidence and figuring out how to express it well to users. So that is the end of my talk. Obviously, lots of people to thank. And you can find out more at the URLs on the screen. Thank you.
on to the next speaker, if people have a few questions for Jeff that are specific to the work that he just presented, we can definitely do those now. So feel free to raise your hand if you have something you'd like to ask. Yeah. The microphone's going to come for you in just a second.
Hey, Jeff, I just wanted to clarify, in the one where you were taking the pictures of the appliance interface, are you trying to generalize from it or to detect that interface in the future, or are you creating a data set for other people to do that, though?
Yeah, so it's a great question. So we are, at the application level, only targeting recognizing that same interface again, so that that user can use that appliance in their home or their workplace or wherever. I think as we deploy the application, so we're hoping to do that within the next few weeks, our goal would be to collect a data set of these appliances so that it could potentially generalize. So again, kind of following this path of deploying the crowd-powered system so that we can both collect data and understand what's important, and then hopefully engage with computer vision researchers to make that more and more automatic over time. Thanks.
Hey, great talk. I was just wondering, are there any other capture mode than taking a photo, right? Because that apparently, seems like the wrong modality for a blind person. I'm just curious.
Great question. So yeah, taking a photo is hard, so why don't we do something else, right? So certainly we and others have explored things like video or streaming video as a way to capture information. I think it's probably difficult to get out of the visual realm altogether because that's kind of what we need to provide access to. But making it more error resistant is various ways of just having them kind of scan the phone around so that it doesn't matter exactly what they're looking at as long as sometimes they're looking at the right thing. And the other thing I should mention is that I've mostly been targeting completely blind users, but people like Shiri Azenkot here in the audience have looked at technology for low vision users, for instance. There you can much more, again, playing off this theme of, it's not just the technology that has to provide the answer, it's the combination of the user and the technology. How do you leverage the vision the person has to help maybe capture the right information so that then some other system or the user can provide more information?
Looks like one more question over there.
Jeff, thank you. This is great work. I hadn't seen this before. This is fantastic. I understand surveillance concerns, but is anyone looking about utilizing cameras in public settings and maybe Minority Report-esque, but essentially zooming in and tapping those cameras to solve the problem of a blind person trying to take a picture, but understand their orientation and take advantage of that infrastructure?
Yeah, that's a fascinating question. So we have another project that I did not talk about here today called Sensors, in which we are deploying many of these cameras and using a crowd and computer vision approach to help understand them, interpret them. I think probably right now the reason not a lot of people are doing that is just because the access to the cameras are probably there increasingly, but access to them is difficult. But it's a fascinating idea of how you could leverage the public cameras and infrastructure as well.
So this is probably related. This is Richard Banks. I run the design team for the MSR Cambridge lab. I'm wondering what contexts blind people are uncomfortable taking photos. So is there a lack of faces, for example, in your corpus and so on?
Yeah, it's a great question. So it's interesting to look at, despite the fact that we have very clearly told the users in our studies that the questions are being sent off to people, what they choose to take photos of. We ask them not to take photos of people's faces or other personally identifying information. Sometimes it appears that they decided to do that anyway, and that might be because they were in a setting, say a public setting, where they didn't think there was a problem in doing that. It might be because they were making kind of a privacy information access trade-off, which is really interesting, right? So the credit card might be a good example of that. I don't necessarily want my credit card up on the web, but at the same time, I want to know what the numbers say on it. And so how do I make that kind of a trade-off? And of course, also because of these problems with taking good photos, it's also the case that you can accidentally capture private information. I think that's the most worrisome for us. And Walter Lasecki here and I and other people have thought about, well, how do you design computer vision or human computation workflows that both leverage the image interpretability of people while still not providing them complete access to an image. We have an HComp paper coming out essentially involving showing them a very highly zoomed in version, gradually zooming out as you say there's no person identifying information in the photo. But it's a hard problem.
Just another question on sort of the capture side of things. Try to capture from cameras in the environment. You could do it from your cell phone, which I guess everyone has. There's also a lot of cameras, like wide angle, very high resolution cameras. I guess there's a big privacy issue. I mean, just a question about, in that sort of space, ideal sort of imaging system for blind photography that balances some of these issues, and the key thing is about privacy and then intentionality, as opposed to always on full resolution to do any task. Like, how do those trade off?
Yeah, so it's a great question. What would be the ideal? I'll say that, especially I think in accessibility, we tend to target commodity devices because I think we feel this desire to make sure that whatever we do, even though we're doing research, has at least the potential for kind of real-term or near-term impact, right? And especially the kind of work here where we want to put it out in the hands of actual users so that we can see what they do with it. Any hardware requirements we make beyond having, say, an iPhone reduces who could do it, right? But beyond that, thinking about what the ideal case is, right? It very likely could be if we had a high-resolution camera, on something like a head-mounted camera that could maybe not always be transmitting, but could save a little buffer so that if somebody had a question about something that they just looked at or were near, they could ask it. That might be good. I think there's a whole lot of other problems that introduces about how do you get somebody to actually wear this camera, like what's the cost of the camera, all these other things. But probably, yeah, better information, more information would be more useful.
Thank you, Jeff. So next, Walter is going to speak with us. And Walter will be talking about the application of AI to hearing and audio accessibility. Let's make sure this is working.
All right. Does that work? Okay, great. And I will see if I can reclaim a few minutes in the interest of panel discussion. So today I'm going to be talking about how we can think about supporting audio accessibility, right, with intelligent systems, and more specifically, intelligent systems that in the near term are going to be crowd-powered. So I'm going to kind of move into a different domain than what Jeff was looking at, but a lot of the approaches are going to be similarly inspired. So if you think about kind of at a high level, there are three different categories of audio accessibility, right? You might have a deaf or hard of hearing user who wants to be able to access speech. So that might be somebody standing up in front of a room talking. It might be dialogue with a peer or a family member. Or it might be some kind of verbal announcement. Beyond that, we also have events that happen all the time. The chimes that are playing out in the hallway to get us all to come in and actually listen to these talks. An alert on your phone, even a fire alarm or something like that would fall into this category of events. And we don't have to be able to understand human language for those, but we do have to understand kind of the context behind that event and when one noisemaker essentially is important to alert a user to. And then finally, even if we kind of can access the audio itself, language can make things inaccessible in its own right. Either the person does not speak the same language as the person speaking, or even the language can be just too complicated. So you think about legalese. Most of us suffer from some inability to understand legalese at one level or another. For somebody with a cognitive impairment, this might be amplified. So what I'm going to focus on today, while there are lots of interesting AI applications across this whole range, and actually even some crowd-powered systems that have tackled each of these, I'm really going to focus today on trying to understand speech and trying to access speech even for a deaf or hard of hearing person. So what's the real goal here? I'm going to be talking about this in the context of real-time speech transcription. So we really want to take a speaker who is standing somewhere in a kind of live setting and be able to understand what they're saying, convert what they're saying to written text within usually about 5 seconds. Less would be better, but if we want to be able to pair what somebody's saying with visual content, or be able to pair what somebody's saying with the ability to actually interject and bring up another point, we need to be really, really fast. So the dream is that we want somebody to be able to pull out their phone, push a button, and immediately get captions. Unfortunately, there are a number of things that stop us from being able to do that too easily. For one thing, speakers vary. One speaker has a different accent than another, different speech patterns, prosody, the actual speed of the language itself. If even the same person has a cold one day and not the next, right, that might change the audio signal that is actually arriving to the system. The environment itself varies. Speaking in this room is very different than speaking in my office. If I'm talking to somebody else, there's a different level of echo, a different distance from speakers, maybe amplification through speakers, et cetera. So we want to think about these acoustic properties and the challenge that they present. Even the settings, even if it's the same place with the same speaker, the microphone might be differently oriented. It might be in a different place. I might be pacing around if I wasn't mic'd up directly. Might be pacing around, and kind of the direction of my speech will vary. And finally, it looks like it ate one of my bullet points. So natural language is weird. So anaphora and kind of the variability of language adds a lot of complexity in its own right, and really takes the content underlying the signal, the speech signal itself, beyond what the computer can understand right now. But my next bullet point was, if natural language is weird, spoken language is even weirder. We interject things, we pause, we kind of redact what we just said and just say, okay, never mind, not that, and replace it with something else. So we have these even more varied language patterns in speech than we do in just written natural language. Okay. So, great. So we're going to take a crowdsourcing approach to bridging this gap. So we cannot currently use automatic speech recognition to solve the captioning problem in realistic settings. There are plenty of cases where I can pull out my phone, I can transcribe a short sentence or two text message. It works pretty well. It even works these days with, thanks to deep learning, pretty well in slightly varied environments. But it's still the same microphone, it's still the same speaker. And if you start to change a lot of the types of the challenges that we saw on the last slide, which really do come up when you want a student to be able to walk into any lecture or room, put down their phone and be able to get captions, it's really beyond what automatic speech recognition alone can do with high accuracy. So we're going to think about the crowd as a way to bridge this gap. And the benefit is that people understand speech pretty well, by and large. Some of these variations can affect people's ability to understand it as well, but by and large, we communicate with one another smoothly in person, and that's essentially what we're trying to capture here. We can understand the meaning behind the language. We can understand how the conversation evolves. When I think Barbara's keynote gave a great example of an interjection that we wouldn't actually use the yelling at the kids as context for the rest of the interaction. So people are really good at this. The problem is there's actually kind of a motor limitation. If we want people to sit there and type out what they're hearing, you can't type fast enough, right? It would require thousands of key presses a minute, and on a QWERTY keyboard, it's really not viable right now. So the accommodations that are available right now for providing speech access are typically highly trained professionals who are using a special keyboard. They've trained for years to be able to type fast enough and kind of listen and type at the same time. If I give this task to an average person, just pick somebody from the audience, which I won't do, I promise. You usually get about 10 to 20% of what's actually being said. And the real problem is, previous to this work, we didn't know what to do with that, right? Having 10 people type different pieces of a conversation does not yield something that's actually useful as an accessibility tool. I can't provide somebody 10 streams of partial information and say, well, good luck with it. We actually do know that people can eventually reconstruct these things, but they can't do it in real time. It's too confusing, it's too messy of a task. So that's where we want computation to be able to help us coordinate. So we have this system called Scribe, which is a tool that allows a student or somebody in the classroom to pull out their phone, stream audio to our back-end server. The server then actually distributes this work of captioning what the audio contains to a set of crowd workers, so we're distributing the workload over multiple people. And then the challenge becomes, how do we get that work, how do we get those partial captions back into one piece? So we're going to have a merging process that then is able to return a single stream of audio captions in about 3 or 4 seconds. Okay, but like I said, this is hard, so how do we actually get people to do this? Instead of asking everyone to just type stuff, we're going to take, at the high level, kind of a round-robin approach. So each person will hear a short segment of audio, maybe 2 or 3 seconds long, right? One phrase, essentially. And they'll start typing out what they heard. Now, it will take them longer than the 2 or 3 seconds that they actually had to listen to it for, which is why this is hard in the first place. But while they're typing, we'll have somebody else come and type the next 2 or 3 seconds, and so on and so forth, and we can kind of vary this based on the size of our crowd and actually reduce the workload on each individual. By the time other folks in our set of 3 crowd workers here have completed or have heard their segment, then the first person has completed their task and actually can take another 2 or 3 seconds of audio and start to type that. So everybody's kind of leapfrogging over one another to type small pieces at a time. And so the interface for doing this is relatively simple. So they have workers come to our task. These can be students in a classroom. These can be Mechanical Turk workers that we recruit online. They can be any other kind of crowd platform or group of interested people who want to help caption. And they're able to type in this interface. So you can see a couple things. One, there's some feedback on if they're doing a good job. So if we recognize that multiple people are, for the same segment, typing the same word, then we kind of lock it in and we confirm that that seems like a reasonable thing to say. So we get kind of long-term running feedback through the points. This animates upwards, so you see what was typed in the past, but it slowly fades away over time. And one interesting thing is that we actually have this text locked in. So I mentioned having latency of only a few seconds really matters. What we don't want is people going back and spending a lot of time editing every little typo that they make, right? So instead, we encourage people to just type through, get what they can, and if they miss something or if they type something a little bit incorrectly, don't worry about it. And what we're actually going to do is have multiple people complete the same segment now in parallel. And by doing that, we can actually run a multiple sequence alignment process over the results, figure out how the different captions can be stitched back together, and then merge that into a higher quality caption than any one individual could have created alone. So unlike kind of the VizWiz model where you're getting multiple different answers from different people, and as long as one of them is good enough, you're set. Here we actually want a synthesis answer that's better than any individual in our crowd could have generated alone. And so this actually performs quite well. We're able to recall about 95% of what a speaker in our data set was actually saying, and we can merge it back together with about 87% precision. And importantly, we can do this all in with a per word latency of just under 3 seconds. So this is actually on par and sometimes even better than professional captionists. And it's because this workload has been distributed over so many different people, right? Now everybody doesn't have to be lightning fast for a long period of time. They just need to be able to type their few words quickly. Okay, now for those kind of doing the numbers on their hands at home, if you say, but I thought speech recognition was 99% accurate in all domains. Well, the problem is, so it's not in the domains that we're looking at. Untrained on a speaker, in a new setting that we just kind of chuck it into on demand, we were getting less than 50% accuracy at the time of this work, and this was a couple years ago. At this point, I'm sure that number will have improved, but we're still not seeing anything near 90% in these kind of Wild West domains of anywhere you start transcribing with your phone. I suppose I would wait to see. Never mind. So great. Now this general structure not just provides us a way to actually get captions to deaf and hard of hearing people immediately, right? We've actually been able to demo this at the CHI conference where we had people in the audience participate as captionists, right? And actually we're able to provide captions for the sessions that were going on. But it doesn't just give us the ability to solve this problem today, it also gives us kind of a framework for scaffolding the development of better AI. So one nice thing is we're assuming that each of our contributors here is imperfect, right? And it doesn't, we're not making any assumptions that they're human. We could add error models and things like that, but we can also throw in an automatic speech recognition system, right? As speech recognition gets better, or if we hit a domain in which it actually performs pretty well, then this one automated unit in the middle might be able to produce most of the captions with high accuracy, right? And as this becomes true, we can kind of diminish the amount of human effort required to accomplish the task at hand. Okay, and we can do this without relying on the system being perfect, right? It doesn't need to either work or we have to use 100% people, right? We can mix these two. It could be a pretty good system for speech recognition, which saves us from having to have two other workers, maybe one other person is enough to fill in the gaps and correct the errors and so on. All right, so kind of in summary, this shows us a way that we can actually create systems that let people collectively outperform any constituent individual on streaming tasks. And this is more general than just audio. We can think about the same kind of alignment methods on any stream of discrete input. We also start to lower the barrier to actually helping with this task, right? Before, you were either an expert or you weren't helpful. Now, I can get a bunch of people together who have the ability to just type at a regular speed, and collectively they can contribute to this problem. This means that now friends, peers, fellow students, loved ones, caregivers, whoever else might be able to actually provide support because of what we're able to do in terms of aggregating and synthesizing their input together. This also means that we can pull in domain experts, right? If you think about somebody who has trained their entire life to be a captionist versus someone who is a fellow student in the class, for a general class, right, like just pick one out of a hat, the student in the class probably has a lot more domain expertise on understanding what's going on, what's being talked about, what the term actually was that was being said, or what was meant by something that was said incorrectly, or pronounced incorrectly. And now we can actually leverage domain experts, not just kind of task experts. And finally, as we saw, this provides kind of a way for training ASR systems on the fly that we can use to generate essentially living data pipelines, right? Now we can deploy these systems first, get them in place, helping people, and then the only thing that changes over time is the intermixing of how much human support is needed and how much AI can do, instead of saying, look, we can't provide that service or that access technology until a certain point down the road where we have the technology to automate it well enough. All right, so on that, thank you.
So again, if we have any questions that are specific to Walter's presentation, we can take those now.
Anthony Hornoff, University of Oregon. Nice work. Have you thought about using cognitive modeling to split up the text? Because there's a lot of great typing models, for example, out there that Bonnie John has done. I mean, I'm sure you have some means of chopping them up most effectively or most efficiently.
Yeah, so we certainly have the kind of infrastructure in place for taking these kinds of models and trying to figure out how to chunk units that people could more easily understand. Certainly if you capture a phrase, right, that's going to be easier for one person to caption than it is if I give you really an arbitrary segment. I don't have numbers for you offhand on exactly what the right approach is there. We've kind of anecdotally played with a number of them. But I think there's a lot more interesting work to be done there.
If you were to use models, you could then potentially parameterize them, for example, for individuals' typing speeds.
Right, yes, and so we have done some work on adaptively learning how fast each individual types and customizing the length of the segment to there, but we still don't do anything to try to plan ahead on like kind of the shift to figure out what the exact phrase alignment is. So yeah, but thanks. Oh.
Hey, really cool work. And I really like this point you made about it might be generalizable to other things. It sort of seems like maybe a framework for generalized multi-threaded crowdsourcing or parallelized computing, something like that, or human computing. In that sort of a setting, it sort of seemed like, one part that you've addressed here is sort of like how you parallelize, right? You take a task that's, requires more computation than a single person or more throughput than a single person has and break it up for multiple people. It seems like in that setting also, a generalized setting for doing that kind of task, error correction would be sort of a key part. And one part that I was a little surprised that you didn't talk about, or maybe you could comment on it, is that it seems like after you've generated this, then it would be very natural to have a person read through and then correct or comment or annotate errors or things that need fix-ups. Any comment on that?
Yeah, so we have played with having kind of near real-time processes, so not within this 5-second bound, but thinking about, well, what about 15, 20 seconds later, right? If we can get rid of all of any errors that were left in the initial transcription, so I think he wants the mic back. That would be one way to think about the secondary process. The other thing is actually using ASR as the initial base source of captions and then having people follow up and do the corrections on the fly. And that turns out, the short version is, that turns out to depend heavily on how accurate the speech recognition system was at the beginning. So we have some work that shows past some threshold, you can actually add benefit by having people just fix what the computer guessed, but below that you actually slow them down worse than if you hadn't given them anything at all. So it's kind of a careful trade-off that has to be made.
Maybe just a quick follow-up on that. So, if you break it up into partial sentences and get people to transcribe those and then put them together, it just sort of seems like the whole sort of semantics around a whole sentence, like no one has access to that. That would seem like a very natural first-order error correction that seems to be missing in a system that only works on partial sentences? Or is there something that corrects for that naturally?
So there's actually, there's an important piece there where we don't actually, for the segments that you're not asked to type, we don't actually hide that content. So it is important for people to listen to the entire audio stream, even if they're only responsible for typing pieces of that. And again, just kind of anecdotally, if we slice up the audio into actual 3-second segments and then mute everything else, people start to make a lot of the same errors that speech recognition does, right? Because they're basically just working from the signal.
Again, this is great work. One of the questions is, now that you have a team approach this, could you combine that with voting approaches? So is there a way of getting people estimating affect? So you could try to get whether people are being sarcastic or giddy or deadpan, and if you have multiple people transcribing, now you have multiple votes.
Right. So we've done a little bit of that, actually. So we have a tool called Glance that actually allows you to do behavioral annotations on video. And there it's the exact same kind of thing where we try to figure out more accurate bounds on the event than one person could come up with, but then we can actually aggregate the subjective judgments that they're issuing for each point, which is available soon.
Bruce Walker, Georgia Tech. General question, when you have more and more volunteers or workers in the crowdsource, sort of following on Beth's point, you could have different people having different expertise, right? So you could have people who are familiar with that accent. You could have people who are familiar with that terminology or that jargon or that domain. You could have people who are familiar with and are tasked with getting the affect or sarcasm or any of these other local regional jokes or anything like that, and all be doing that in parallel and then stitching that together. So as a general comment to you and to Jeff and others, is that being done? Is this sort of splitting up the crowd into sort of expertise subsets and then stitching it together? Is that something we're seeing yet?
So we're starting to see a little bit of focus on expertise, usually more holistic experts. How do you bring an expert who knows that role to a job that only they can do? Here, it's a little bit different, right? You have a different modifier on your expertise. So you're able to type, but also you know something about the dialect, or also you know something about the content. I think right now that has mostly been relegated to a recruiting problem. So how do you find people who would fit together? You might use the same approach. That would be a little naive to actually maximize benefit from that. But I don't think there's been as much work at this point actually focusing on how you use those modifiers on expertise. Yeah, it's a good idea though. We're thinking about it from the tool side though. How do you divide the tools up and then give everybody a different type of tool to accomplish the same task? They all come back with something. That's essentially inducing that variation. Yeah.
Hey, Walter, I'm curious whether when I'm typing on the piece that I'm transcribing and I'm starting to hear the next bit, does that interfere? And have you thought about actually muting it and then playing fast to catch up so that I have kind of focus and then I catch up to it?
So what we do right now, yes, it does throw people off a little bit at those boundary words. What we tend to try to do is be very inclusive and just say, if you weren't sure exactly where it marked the ending of your segment, just include it. But that's only a fractional answer to your question. So what we also do is, usually instead of muting it altogether, we give you that little bit of focus by decreasing the audio level, right? And so you get a very salient, in the same audio stream, you get kind of very salient indicator that you are not responsible for the content that you're listening to now, but are able to kind of follow along as much as you can listen. The other thing is that we've done exactly that. We've slowed things down and then sped them back up. And it turns out that this can actually change the behavior that people exhibit when they're captioning. And so we can get kind of double-digit improvements in precision recall and, surprisingly, latency. So we get faster when we slow people down because you're able to keep up per word instead of like kind of memorizing that segment and typing it later. So yeah, great point.
Great. Thank you, Walter. All right, and next up, Sean Kane from the University of Colorado is going to talk about speech and communication disabilities and the applicability of AI to those domains.
Now, I told the camera crew I was not going to stand here, I was going to stand over there, but I changed my mind, so sorry about that. Hi, everybody. So thanks for having me here, and as Mary said, I'm going to talk about how we can think about AI and to support people with a wide range of communications impairments and disabilities. And if you take anything away, my point is to say that this is actually a problem where there's so much opportunity to actually address issues, and that looking at how to support someone who has difficulty communicating about the world around them, there are interesting subproblems in almost any area of CS research in terms of understanding the environment, in terms of understanding language, in terms of HCI and user input and output. So I'm going to just talk a little bit about some of the problems, and I'll tell you about some of the work we've done to date looking at some of these issues. Start with a very brief vocabulary lesson to orient us all and to give you a sense of what are the sorts of technologies that are already out there. And so I'll talk about AAC during this talk. So we say AAC is augmentative and alternative communication. If you have any experience with this technology, you might see something a bit like, sorry, my laser aim's not very good. But this symbol-based menu you'll see at the top there. So for someone who might have difficulty typing or writing, you can have symbol-based communication. We also see more typing-based input, and I'll share some examples of that later on. And I just want to point out that there's a wide range of what sorts of technologies and what sorts of interactions you might see using AAC. And to give you a sense of the population, so estimated about 2 million people in the US, so a little bit less than 1 out of 100 people would be severely communication impaired and would need to use this sort of technology for their everyday life. And again, when we think about who would actually use this, we see a really wide range of challenges. So we think about physical disabilities, so maybe severe ataxia speech or ALS, where the cognitive abilities are not impaired, but the ability to actually articulate speech is. We've done some work looking at linguistic conditions such as aphasia, which may or may not have a cognitive component, but mostly have a component around processing language. We also look at cognitive and intellectual disabilities, autism spectrum disorders, and so forth. So again, when I say there's a lot of different subproblems here, you can imagine just looking through this set that there are quite some differences in terms of how you would actually do this. And in some of the work, we've looked at, well, how can we apply some of this work outside of people with disabilities? So if you think about typically a functioning adults who might be learning a new language, we might learn a lot about efficient text input and communication could be useful in AAC, but also in the general population. And just to give a sense of how this impacts people, so often if you have a more severe communication impairment, this could be the barrier between participation in public life or the lack of there. So going to work, school, traveling, and if you are unable to communicate, you're often unable to do these things. And this can be despite the ability to do so, right? So if you have the cognitive capabilities but aren't able to articulate speech, you're not going to be able to participate in these ways. And some of the work we've done recently, and in collaboration with Marion with MSR, we're looking at the effects of communication technologies on one's identity. So if you, we've done some work with people with ALS, for instance, and if you think about, for example, like how embarrassed you might be if you call someone by the wrong name, or what people might think if you do so, all of these issues can affect someone who's using AAC even more so. So it's important that you represent one as a competent, independent adult, and to represent one's own personality. This paper here talks about some of these issues. And again, this technology can be the difference between participating in public life and not. Here's an image of Steve Gleason, who has ALS, and he says, until there's a medical treatment or cure for ALS, technology can be a cure. And you can see in this image, he's eye typing using an eye tracker. So we've done some work looking at particular people with ALS who have their full cognitive capabilities, linguistic capabilities, but aren't able to move the rest of their bodies. All right. So to give a sense of how this is actually could be useful and how AI can help address some of these issues, as I said, there are a number of sub-challenges that are quite interesting, and there's quite a lot of opportunity here. So if we look at the challenges of human-computer interaction challenges for AAC, it can give us a sense of how we might address some of these issues. And if you think about your typical everyday communication, the goal is to be able to support real-time communication about any possible topic, right? We might start talking about communication in AI, but if the conversation goes in a different direction, we want to be prepared for that. There is some significant input challenges and throughput challenges around AAC. So, for example, if we look at eye gaze typing, most studies show about 20 words per minute input, versus in typical conversation about 180 words per minute. So there's just not only a quantitative gap, but a really qualitative gap in terms of one's ability to communicate. And as I mentioned, some of the work we've done recently is looking at this notion of authentic communication. So it's not enough just to say the right words, and even in the right order, but we represent ourselves through our communication. So it's actually quite important that how we express things affects or reflects our mood, who we are, what we see as our personality. And the real opportunity for AI is in understanding the context. So understanding the context of the person, of the environment, and their communication preferences. So I'll share a few brief examples on how we've actually used context as a way to enable more efficient communication. So if we look at some of the factors we might think of, we need to know a lot about the speaker. So we might want to know their conversation style, what they know, what they're doing. We also often want to know about the conversation partner. And a lot of work to date has looked at this issue of environment. So how do we understand what's happening in this situation to help us enable more efficient communication? And as with Jeff and Walter's work, we have looked at humans in the loop. And we might think of humans in the loop as being a good way to solve some of these issues because humans tend to be very good at communication. So we've looked at, for example, annotating images of the environment and having humans suggest what someone might want to say about that. But as with the other examples, there are some issues where humans in the loop are just not going to work very well. So if we think about conversations about private and sensitive information, there are going to be some conversations that you just don't want to have anybody outside of that conversation aware of it. Again, this issue of latency. So if we have very fast spoken conversations, what we've seen in our work to date is if someone can't keep up with this rate of communication, often the result is they withdraw from conversation, right? So if everybody around you is speaking at 180 words per minute and you're speaking at 10 or 20, it's really difficult to participate in that conversation. And what we have seen is it is very difficult for everyone else to adapt to that style of communication. So we often just see people withdrawing. And I think there's a big argument for all populations of people with disabilities, but here of the notion of independence. And if we're using technology to support independence, it's different in many ways than having a person in the loop. All right. So I'm briefly going to describe two systems that we've developed to look at some of these aspects of context. And there are links to papers so you can learn more about them if you're interested. And so again, if we think back about the ways that the context that we're in shapes our conversation, some of the early work in this area really looked at where we are and who we're talking to, right? So a lot of what guides our conversation is about who we are interacting with. And to look at some of this, we developed a system a few years ago, which was looking at how do we actually include this in the interface. So this is work with people with aphasia and
school.
Well, that was, oh, sorry about that. There was audio in that video.
Company.
Actually, can I mute this? Sorry about that.
Room.
Do you know how to do it?
House.
Oh, can you? Oh. Sorry about that. Oh, thank you. Yeah, so the environment can really affect our ability to communicate clearly. And so this is work looking at people, working with people with aphasia. And as I mentioned before, there are quite a lot of individual differences in terms of how we think about designing these tools. In this work, one of the strong pieces of feedback we actually had was looking through menus and interacting with the interface is extremely taxing for this population. And so if we have a system like this that's a symbol-based communication tool, well, we want to enable a lot of conversation topics to talk about whatever you might like, which means very long lists of things that you might say. And so the work here is to look at how can we actually design an interface that will trim down the options or allow the person using the technology to focus on technologies of interest. And so if you go to this link here, there's quite a lot of description about how we developed this system, got feedback. One of the challenges I'll talk about in a minute also is collecting feedback from people who are severely communication impaired, and collecting data in general is a real challenge. And so we looked at this concept of using location and people. This general framework was well received, although there were a lot of challenges around how do we actually enable the user to switch between contexts, and the trade-off between automatically adapting the context, which is easier but confusing, versus more manual selection of, I'm talking to Mary and now I want to talk about Harry Potter, for instance. So we developed a few different versions of this system. There's actually also some really great follow-up work from Kristen Williams and Leah Finlater, where they've looked at similar techniques on different form factors, so like a head-mounted display. And the other work I want to draw your attention to is thinking about local environment as context. And this is an interesting case where advances that are happening in other areas of AI and even AI for accessibility give us some opportunity for enhancing communication. So we see here an image of the produce aisle at the supermarket with terms tagged, and then it's a little difficult to see, the text is a bit small there, but discussion prompts around those objects. So we just presented this work at the DISC conference about a month ago, but we were looking in particular at how do we, in this case, how do we support people with eye gaze typing? So these are individuals with ALS who, again, have full linguistic or cognitive capabilities, but have this really, really, really slow input rate. So how can we make the system predict better what I might want to talk about? And we might say that the objects in our environment are a source for that. So I'm going to talk about this water bottle or the remote or what have you. And so we built some prototypes that used Microsoft Cognitive Services and the cameras on the speech devices actually to capture objects in the environment, so that then you could use this as either prediction for typing, as you see here, or separately as a way to generate full sentences. So if we get this part right and we can actually generate a full sentence that is something that someone might want to say, we can drastically reduce the amount of effort required to communicate. And so this link here will tell you more about the paper in terms of how we developed this system and some of the contexts where this could be useful. All right. So I want to wrap up just by directing our attention to some of the opportunities and challenges here. So our work here says that there's quite a lot of potential in having communication devices that are smarter and that know more about the environment. But there are some significant challenges. And if we look at the previous examples for accessibility for vision and for audio, we see that there's quite a lot of work in understanding what's going on. Here we have the additional challenge of taking that and turning it into something that's actionable. How do we understand, how can we communicate about this? What you might note from these examples is we do have this challenge around collecting feedback and collecting data. So there are some really interesting problems here around how do you understand maybe how these minor variations in a user interface or in a prediction algorithm can affect a person. Well, this can be especially challenging if they communicate very rarely and slowly and with quite a lot of errors. So both collecting the data to help us understand how to build these systems, but also how do we assess, and for the users, how do they assess whether adopting this new tool could help them is a real challenge. So in the context of AI, there are some really exciting problems here again. Anywhere where we can increase our understanding of the environment, we can use this to help support communication. So any new channels that we might have in terms of understanding the context, understanding a conversation or a group of people. And there are some interesting opportunities around fusing these different contextual data sources, right? So if my system detects that I have a book, the conversation around that book is going to vary quite a bit depending on whether I'm at the library, whether I'm in my book club. And again, this notion of authentic communication. So once we understand what's going on in the environment and what types of interactions we might, an individual might want to have, this challenge of now how do we present that in a way that's authentic to how the person sees themselves and how they communicate. And finally, this challenge of how do we assess interventions and how do we guide design with limited data and limited feedback. So to end this talk, I'll just say I think this is a really exciting area. I hope you'll take a moment to think about maybe how some of your work could be adapted to this space, and move on to the rest of our Q&A. So thanks.
Thank you. And again, if people have questions specifically about the speech and communication devices, let's take those before we move on to the whole panel.
Thank you very much for a great talk. I'm Helen Mang, Chinese University of Hong Kong. I'm curious, you mentioned about expressive AAC, and you gave the example of having a conversational partner, an option of choosing which conversational partner, but you also mentioned using emoticons and social context. So I'm wondering whether, what kind of social context are you thinking about? How to categorize that?
Well, one thing we've seen in some of the work we've done in interviews with people who use speech-generating devices and their families, there are real differences between, for example, if you're communicating with someone who understands working with someone with this kind of disability versus not, and that's quite different. One thing we saw in some of the work around people with aphasia is the amount of preparation they would do. So if you were going to talk to someone to say, oh, hi, I have aphasia, you might have this written on a card. It says, I'm intellectually capable, but here's how you communicate with me. So there's some setup there in terms of maybe understanding known versus unknown. And then we've also seen some challenges around group size, and that really affects the ability to communicate. So there's some around the structure of the group, and also where we can leverage conversational scripts. That's always an opportunity. If we know, if you go to the supermarket and you check out, the speech transactions are pretty universal across every time you go to the supermarket. So if we can accelerate some of that, that could be an opportunity as well.
So, hi, Sean, very nice work, thank you. So I'm trying to understand Scene Talk a little bit better. Assume you have a corpus of 400 hours of YouTube videos or how-to videos that have subtitles and that have the objects that you can see in the video saying, oh, this is how you operate a printer, this is how you change the wheels of a car, and you can recognize that there's a wheel, there's a car. Would that be sort of the setting that you think about, or would that be interesting?
It could be as a source of input. So here in this case, where we're thinking about actually having the camera on the speech-generating device, and so capturing everything around you and using that to start conversations. I think one feature that would be useful is just more data about the kinds of interactions with objects. So can we actually understand, one piece of feedback that we saw is, I can recognize that this is a coffee cup, but actually the interesting thing is not to say coffee cup, right? You actually want to say like, oh, this coffee is really good, or oh, I'm so tired, I really need this coffee, right? So there's a lot of human-to-human communication that, and there are data sources that we can look at. So we looking at mining news stories or mining fiction or other kinds of things could help us understand interactions around objects.
Right, but the important thing is that the thing that the person is talking about is visual, it's visible in the surroundings, and you have a camera stream, and anything that supports that would be sort of what you're talking about. Okay.
Yeah, and one thing we haven't looked at directly yet, but is how do you position the device? Again, we're often working with people who have severe mobility limitations as well. And so if the camera is not capturing the object, then what other things can we use in terms of maybe inferring? If I see one object, then this is often we see this as well, or those kinds of things. So increasing that understanding could really increase the benefit of this kind of system.
Any additional questions? Oh, great.
Hi, I'm Melanie Friedoken from Oregon Health and Science University. And you raised the question of access. So are you just dealing with direct selection either through eye or through pointing right now for people with physical impairment?
Yeah, so for these systems, in the first example, we used touch, and then in the second example, it was eye gaze input. And so this was one of the challenges that we've seen is how integrating these types of prototypes with the systems that people are using. And so there's a lot of extra effort in terms of if you have someone, for example, using switch access or some other type of input. I think we're still thinking a lot about how do you actually get this technology out in the field, even to collect data, not necessarily as a full-time solution. Does that answer your question? Okay.
Great. Thank you. Now, just bring this back up. So, slideshow from current slide. So I put together some questions that I thought might be interesting for the panelists to discuss that bridge all of these themes, and those are up on the big screen. But I think before we prioritize the questions I thought of, it's better to prioritize the questions the audience might have for the panel as a whole. And if any of these ones strikes your fancy, then feel free to reappropriate it or modify it. So if you have questions that you'd like to ask the panelists more generally about AI and accessibility, please raise your hand and the microphones will come around. And indicate if you want the whole panel to answer or if you're directing to a particular person.
I got the microphone. Hi, this is a question for the whole panel. I think this panel was about using AI to support accessibility. And I'm interested kind of in an opposite question, which is that as devices are now having AI capabilities, how does that exacerbate the accessibility issues? So for example, cars used to just have buttons and dials and things like that you can touch, but now there's a whole tablet in front of you, and also algorithms might want to communicate something quite complicated that they can't do with speech, right? Maybe they want to show you a graph now about how it makes a decision. So how are we going to deal with those for vision, speech, and communication issues?
Well, I think every new technology era has tended to introduce new accessibility problems. And unfortunately, too often, we're playing catch up. I think it's increasingly true that, at least in research, there is a growing field that is kind of tackling these things potentially a little bit earlier. I mean, we're still behind. So, every new Internet of Things device that decides that it's cheaper to have a speech input rather than a screen, for instance, is likely inaccessible to a deaf person. And so, we have a project now that is trying to play catch up there on how do you enable a deaf person to interact with an Internet of Things device that only accepts speech. But those devices are already out there, right? Or the work that I presented about the appliances, right? It's fancier now to have touchscreens on everything, but those touchscreens are smooth. And even though the iPhone has all this really nice software on it that allows accessibility, most of these cheaper, your microwave probably doesn't, right? And so we are playing catch up a lot, and it's not clear how to change that. I think in certain domains, right, there's certainly legislation that's happening that's making it so if you go into, say, an educational institute, at least theoretically, you have to be accessible, right? So that might be one answer. There's technology that's been developed that's more general purpose, right? Like seeing AI is coming out, which is cool, and like other things that might make it so that you can use technology to solve the inaccessible technology problem. But it's still a problem, and we don't have a good way to get ahead of it, which I think would be the dream of a lot of us.
Yeah, I would add to that. I think with AI systems in general, all AI systems make a bunch of assumptions, right, about the user or the environment, or they have models, right, models of the user. And these systems are only as good or generalizable as the models are. And if the people designing AI systems forget about the 20% of the population that has different sensory or motor or cognitive abilities, then the models will not be accurate for a large subset of users. And I think that that's an important problem for us as leaders in this field to keep in mind and make sure that we kind of get ahead of in what we build.
Yeah. So adding to that, I think the idea that you have to design for a more, you kind of have this idea of universal design or accessibility-based design for AI systems in the same way that you would for existing systems is certainly going to be true. I think where there's a little bit of hope, to me at least, is that a lot of, at least in interaction, what AI has been targeting or promising or whatever you want to phrase that, has been a more naturalistic interaction, and usually that cuts across more different modes. So we have a little bit more flexibility in some sense in some of these newer technologies, that if the system's really intelligent, right, then we can be more adaptive. We can better fit what the user is actually able to do with the interface in a way that maybe wasn't true when the microwave went to flat buttons, right? The buttons kind of provided no additional way to adapt in a way that the interface otherwise couldn't. So there's maybe a little bit of silver lining there, not just new stuff, but new, more adaptive stuff.
All right, I just actually wanted to add on to what Mary said a little bit, which is around collecting data. And one problem that I have encountered is, even if you collect the right data, often we don't necessarily know how to include that in our system, right? Is it a question of a separate accessibility mode, which we've been moving away from the last few decades, or how do we think about, even if we have this data and we're able to get it, what we can do with it? The other concern that I will point out is a lot of people with disabilities and chronic health conditions rely on this existing infrastructure of therapists and medical practitioners. And I think we saw a bunch of examples here that were direct between the technologists and the end users, and there's a lot of benefits to that, but there's the concern of we might actually lose these expert practitioners who might not be able to keep up. I know one thing I've seen in some of our work is when we include therapists or other subject experts in the problems, they're often extremely conservative about trying things out, typically much more so than the end users, and are favoring things that are simple and really understandable. I think Melanie really wants to say something.
I just wanted to add on what Sean said, one other thing, which is I think that his point about data is really good, because the generalizability of AI systems are sort of only as good as the data that we collect and train on. And as a specific example, I think going back to what Jeff said, so lately there have been a bunch of advances with deep learning in computer vision, right, and being able to take photographs and identify the objects in the photographs. But those systems are trained on high quality photographs, right? So those systems, for example, even though there's this desire to make applications where someone who's visually impaired could take a picture and then have the contents of the picture labeled for them by artificial intelligence, people who are visually impaired take very low quality photographs typically, and the vision algorithms are not trained on the type of low quality photographs that people who are visually impaired take. And so until you kind of broaden your training data set, you're not going to be able to accommodate that use case. Yeah, Beth.
Again, this is a terrific panel. I'm so excited to see this work and Microsoft's embrace and encouragement of all this. I was a little surprised, and even going back to your first slide of all of the different categories, that aging is not part of this agenda. It's important to recognize that the National Institute of Aging has changed the definition of what's considered normal aging to include management of chronic diseases or other types of impairments. It's a really interesting combination of many of the things that you talk about, and could obviously increase kind of the scale and impact of what you're doing.
I agree, and actually that's just an omission on the slide. I think aging is an example of something that cuts across all of these different categories of sensory, motor, cognitive. And just as I was mentioning that maybe 1 in 5 people have a permanent disability, but there are also temporary disabilities like breaking a limb or situational impairments. Aging is another example of the broad applicability of this issue because hopefully all of us will become older, and as people age, you begin to acquire different disabilities. And I think overall the aging population, especially if you look at the population curves in places like Japan and the United States, where we have a large segment of the population that's aging relative to the younger population, thinking about how AI technologies can help support, for example, aging in place and longer duration of quality of life with respect to your lifespan is a really important challenge that we should all care about because it's going to impact all of us at some point.
I'm kind of curious how to think about integrating these AI technologies into your research as it evolves. So I thought Walter had this interesting point of if you inserted the speech recognizer as another one of the crowd, because these technologies are changing really rapidly, and so unless you're like deep into the AI, sometimes you might not know. So the difference in quality of speech recognition from 2011, when you probably did that work, versus today, I mean, it's still not perfect, still doesn't always work, but it is dramatically better. We've done studies where we saw, at least for short text messages, 3 times faster than people typing, and not making many errors. So I'm curious how you start to think about, same with all those vision systems, how do we include the systems and regularly update it to see how would our algorithms change if the AI technology hit a different threshold, and is there important thresholds when it gets beyond something that it changes the whole architecture, how you think about it? It seems like for a lot of us, we do the problem, post paper, and we move on to the next thing, but it's how would we think about how these systems would evolve over time as the underlying technology improves? And in fact, a lot of your research is how do we get the data sets that would help the technology improve? And so the question is, are we getting there yet where we start to see these systems almost improving as that happens?
Yeah, so I guess as the one who maybe plays with architectures a little bit more on the panel, the idea that we want to create workflows for crowds that actually are more coherent when looked at through the lens of just intelligent contributors, right? Then a black box coming from the speech recognition side of things, we know what role it plays in the system, and as long as it continues to play that role, as long as speech recognition produces text from an audio input signal, then the hope is that we don't actually have to re-engineer anything. It's just a matter of dropping the latest version of whatever the state of the art is into that box. And then it becomes interesting for the more general view there to say, I want to be able to have the system automatically adapt itself, right? So for speech recognition, one of the interesting things that we were looking at in the community was that we do have these professionals, right? We have people who are trained and have trained for years and have kind of worked for potentially decades doing this job at a very high level. They have a mastered a skill. We don't want to just displace everybody because now we can do it with anyone in the crowd, right? We actually want to be able to do, I think in response to Anthony's question, I mentioned that we did some things on adaptation and trying to actually custom fit what each contributor was able to provide. There, we want to actually be able to say that if you come in and you're a professional, we can get more benefit from your effort, and we will pay you kind of a larger percentage of the entire task value. Similarly, as speech recognition gets better, it kind of grows into its place until it simply is the entire system, right? Now, I think creating these architectures is really difficult, so I think that's an open challenge as to how to generalize that fully. We've seen a lot of different examples right now in different spaces.
I'll just follow on to that, especially since my colleague, Florian Metz, is there in the back. I actually share a floor with a speech recognizer. Speech recognition researcher and a speech recognizer. He does great at both of those things. But and I think one of the challenges, especially from the crowdsourcing perspective, is that I think that we do need expertise in these various domains in order to do this well. And so in the case of the speech recognition work that Florian and I and students have kind of continued, it's really hard to figure out a way to get the crowd to effectively work with the automatic speech recognition. The speech recognition systems work very differently. The best results come too slowly for our domain, which is very different. We're also not targeting, typing short messages with text messages, because that works a lot better than it used to. We're targeting this continuous real-time captioning of a lengthy lecture on a topic that the speech recognizer might not even have the vocabulary to speak. But anyway, figuring those things out, I think, is a really interesting challenge, but definitely requires working with the domain experts. And so we're doing that with speech recognition researchers, with computer vision researchers, with dialogue system researchers. It does get a little bit crazy trying to manage all of that. But I think that you're completely right that it's important to do that. And Florian has a comment.
I mean, maybe I want to ask two things. One is, it should be enough for the human to fix a mistake once, and every future time, say, a new name or a new acronym that you just haven't seen during training of your recognizer, be it speech recognizer or a vision system. There's always going to be out of vocabulary things that you write in all caps, and it's important for a human, and the machine might not know this. So a human should fix this mistake once, and then you feed it into the automatic system, and that's the work that we've been doing. Or you just use this information, the feedback from the human, to improve these systems in real time. So that's, I think, the value that these systems still have and will have for the foreseeable future, even if the error rate is getting really, really low. What we're still getting wrong are the content words, or the important words, and that's where the human makes a dramatic difference. Still, even if you have 5% word error rate, if you get the name of the speaker wrong, if you get the name of the MFCC feature that this lecture was about wrong.
I mean, so kind of generalize that. I think it kind of changes the structure a lot of times of the problem. So instead of going from, we've got a data set and we're trying to get as good a performance as possible on this data set, which is kind of the common pattern across a lot of different AI research, we're taking it to, we have this interactive application, and we've now situated it, right? So we have it in this lecture, and we're assuming this student is going to come and, they're just going to show up and they're going to pull out their phone. Well, where does that speech recognition system that's been trained on a static data set fall down? And where it falls down is it doesn't know this out of vocabulary word that's a jargon for the course, or, for example, right? Or it doesn't know this particular speaker, the audio quality is poor. And so how do we change the structure of the problems that the AI researchers are working on so that it meets some of these important kind of situated tasks? I think that's kind of.
Thank you. So I hate to cut off the conversation, but the folks in back are holding up a sign telling you to wrap up. And I don't want to stand between you all and lunch. But what I would say is that, and I don't want to stand between our speakers and lunch either. So what I would suggest is that for those of you who'd like to chat more with the speakers, perhaps you can come up and then go to lunch together and sit and continue this discussion over lunch. And of course, we'll all be here throughout the rest of this event. And thank you so much.